This is the solution set to the energy transformation review. The first questions involved straight application of a single formula. A force of 10 Newton acts over 5 meters. You would just need this formula, put in your numbers, calculate the answer, and don't forget that Newton meters are joules. But what if I give you the mass and the acceleration? Then instead of the most general form, you'll break it down into MAD. Force is M times A. You put in these numbers and you get 840 joules. Now what if you wanted to calculate the speed of the object at the end of this? You can go back to kinematics equations right from the get-go, knowing the acceleration and the distance the acceleration applied, you can get the final speed using this calculation. Similarly, you can get the time using a kinematics equation like this. However, if this work is done, you could also do it straight to kinetic energy. You could do EK equals 1/2 mv squared kind of thing. Then calculate the final speed from that. This one, a 5-gram beetle flies up from the ground to position 10 meters higher. Straight application of this formula, not forgetting to turn grams into kilograms. And you get 490 millijoules, sorry, not megajoules. Doesn't matter where. No, this equation is assuming that this is a delta H, a change in height. You went up 10 meters. Doesn't matter whether you went up 10 meters in Orangeville, which is several hundred meters above ocean level, or you ascended 10 meters in Newfoundland, which is right at sea level. It's the same. 4-gram bullet travels at 990 meters a second. Nothing shocking or surprising there. 90-kilogram skateboarder face plants and stops his forward motion in 2 meters. The coefficient of friction on the pavement in his face is 0.75. Calculate the work done in his body through his face. Well, if we're going to be coming to a halt in 2 meters, it's strictly due to friction. And remember, friction is the surface roughness. Mu is the surface roughness, called the coefficient of friction, times the normal force. And the normal force is the same as the gravitational force on you on flat ground. So that's the same as called weight. So the skateboarder has 882 newtons of weight. You take that and you put it in the friction equation. The surface roughness means that his face is feeling a frictional force that is 3/4 of his body weight. You might want to wear a helmet. An archer draws his bow. That's the spring equation. Okay, notice newtons per meter and the bow is in centimeters. Something needs conversion. A cup of coffee is heated in a microwave and it goes up to 95 degrees. Calculate the work done by the microwave on the coffee, or you could say the energy applied. That's a heat equation. Stick in the numbers that were given to you, and you got it. Now, if I tell you the oven is 47% efficient, which is a number I looked up, then this number here that you needed was only about half of the number that the microwave applied. So you needed almost 90,000 joules to heat the coffee, but the oven wasted half of its energy. So we should be floating around 180,000 joules is what the oven produced. So our answer is 47% of the microwave energy. You have to work backwards. So the total energy the microwave produced times 47% is what went into the coffee. So to get the energy the microwave used, we take the 47% over to this side, and we get our 190,000 joules. And percentage, when you're actually using it in a calculation, change this percentage sign to what it means, 2 decimal places removed. The Saturn V burned 750,000 liters to reach orbit. How much energy was released? Well, what you do is you search for energy density of kerosene, and you'll find you get 37 million joules for every liter. So if we took 700,000 liters, notice I dropped a number, that's okay, times 37 megajoules, I get 2.6 times 10 to the 13th joules. That's tera is 12. So I could use up 12 of these zeros with the letter T, leaving 1 0 left. So 26 terajoules of energy. Einstein's formula lets us theoretically compute the total energy available in a chunk of matter completely if we could convert it to energy. The only way we know how to do that is a nuclear weapon. So I looked up the mass of flea poop, and fleas poop about 0.77 milligrams a day. So a milligram, 0.7 milligrams is 0.7 times 10 to the third minus third grams. This formula takes it in kilograms. So I divide by 1,000 again, and I get 0.7 times 10 to the minus 6 kilograms. This means a single flea poop theoretically has 6.3 times 10 to the 13th joules. In a single flea poop, the Saturn V needed 750,000 liters of fuel to just reach this number. So literally 1,000 flea turds could send a Saturn V to orbit. Or 1,000 flea turds could send 3 Saturn V's to orbit if we could somehow control Einstein's formula and control that energy release, which we haven't. I got some surprisingly hard number to find. I had to find the acceleration of the Toyota Tundra on YouTube. It reaches highway speed in about 8 seconds, which is very similar to the Honda Odyssey. So the acceleration of the Toyota Tundra is this. The distance is what we need next to do force times distance. And we can do this because he's going to reach 28 meters a second from 0 in 8 seconds uniformly. So we can take our average speed again. So we get about 109 meters. This means the vehicle had to produce about 1 million joules to carry out that acceleration. 1 million joules in about 8 seconds is 149 kilowatts. 149 kilowatts divided by 735 kilowatts per horsepower is 202 horsepower. And if we look over here, the Toyota Tundra is rated at 381 horsepower engine. So that's totally doable with this vehicle. Batman has a mass of 100 kilograms. His bat grapple tows him to the ceiling 8 meters high in 2 seconds. What power is the battery providing? Step 1. We calculate how much energy Batman needs to reach the ceiling. Step 2, divide it by the time he took, and we get 4,000 watts on his little bat belt when he gets towed up by his trigger finger. From my own personal experience, I know that a D cell can dump out about 4 watts. So 4 joules a second for quite a while. This means he's going to need 1,000 D cells on his belt to pull this stunt off. So Batman's going to need a car battery or 2 or more to use his bat belt to go up fast. Otherwise, he's just a human pinata sitting there. This would be about as fancy as I could make a question. You wish to have solar power at your cottage of 3,000 watts. How big would the panels be if the solar intensity is this and the panels are 11% efficient? So if the panels are 11% efficient, then the intensity of the sunlight times 11% means we really only get 88 watts per square meter. So we lose an awful lot. The power is going to be the wattage per square meter times the size of the panels. So 88 watts per panel, and we need 3,000 watts. So the 3,000 watts divided by 88 watts for every square meter panel, these are about 2 square meters, would give us 34 meters squared. So you would need about 17 of these panels these gentlemen are carrying there to provide your 3,000 kilowatts, your 3,000 watts. Go away. And that's a $4,400 system. So they say 269 square